Okay, so Fermat's theorem says the following. It says that if f has local extreme value of f of c, then f prime of c equal to 0. Oh, excuse me. Or, well, there's a little. I missed something. I'm sorry. Let me just fix it. F of c and f prime of c exists. That's what I missed. Then f prime of c equal to 0. This is a if-then statement, yeah? So I have a proof in the notes, and it's careful, but like I was telling you in the break, it is a bit technical, and I don't think I've ever asked students to prove that on a test. I would ask it in an honors calculus class or in a real analysis class, but not in here. So that means it's probably not the best use of class time for me to actually go through that in class. But what I should do is give you a sketch of a proof by picture. So this is not a proof, right? But it's a plausibility argument. Let's think about it. Right? You got a function, right? And so this would be a local minimum, right? If we draw the tangent line there, what's it look like? It's horizontal, right? What do we know about the slope of a horizontal line? Slope is slope. What am I writing? I don't know. Slope 0. Right? So it says that f prime, if this is c, f prime of c is 0. And the same argument holds up here, right? At a maximum, f prime, if that's c2, f prime of c2 is 0. Right? So that's it. Now, there is this is not actually how I remember Fermat's theorem. Like the way we tend to we modify Fermat's theorem a little bit as a point of let's say Fermat's theorem plus or something. I don't know. So let's rewrite it a little bit. All right. See, because it says and f prime of c exists, right? Well, think about it. What if the graph continued like this, right? And it had a jagged like that, right? Well, see, that's a place where f prime of c3 does not exist, right? But that point right there, that's a local minimum, right? So we see local minimums are going to happen either at places where we have, zero tangents, zero slope, or also places where the derivative doesn't exist. That's another place where they could happen. So we could say this: f has a local extreme value of f of c, then c is a critical point. Well, critical number, rather. Which again means one of two things. Either f prime of c equals to 0, or f prime of c does not exist, all right? Now, the converse is false. What would the converse be? The converse would be if C is a critical number, right? Then f of C is local extreme. This is actually false, right? Now, I haven't shown you evidence that this is false, but my in-class example will provide us the evidence that we seek. So this is the ICE on page 139. And here we're going to look at f of x equals to x cubed. And we're going to look at g of x equal to the cube root of x. All right. What happened? Oh, the camera. Oh, thank you. Bonus point. I should pay you money. Here, unfortunately, I've only got 20s, so sorry, it's not quite that. It's not quite that. Anyway, so check it out. df dx equals to 3x squared. So c equals to 0 is critical, right? dg dx 1/3 x to the minus 2/3, also known as 1 over 3 cube root of x squared. So here c equals to 0 gives g prime of 0 does not exist. So in both cases, 0 is a critical number. And in both cases, it's neither a local max nor a local min. Now, I'll show you the graph, because I happen to know how to graph these. The graph of x cubed looks like this. See, at 0, there is a horizontal tangent, but it's just pausing before it keeps going up again. So that's neither the biggest nor the smallest for any open interval close to the point. It's not a local max or min. The cube root of x, the cube root of x is even more insidious. Cube root of x looks something like this. If I did it right, it's the same shape, just set on its side. Okay. I just have all kinds of trouble drawing this. But what I'm trying to capture there is that what happens, the reason that the derivative breaks down at 0 is it has a vertical tangent. So vertical tangents do not have to be local maxes or mins, but they are places where the derivative is undefined. So this is why the converse of Fermat's theorem is not true. We must keep this in mind. This is a common mistake that students make, is they get it in their head that critical number automatically means local extrema. But that is not the case. It's more complicated than that. Sometimes it is, sometimes it isn't. All right. We now arrive at a hilarious thing in my notes. I, for some reason, have neglected to put the proof of Rolle's theorem in my notes. What I'm going to do, because I don't know. I could try to prove this on the fly, but I feel like I would just waste a half hour of your time. So let's not do that. Suppose that f is a function such that number 1, f is continuous on the closed interval from a to b. Number 2, f is differentiable meaning the derivative exists, right, on the open interval from a to b, and 3, f of a is equal to f of b. What does all this data get us? All right. Then there exists c in the open interval from a to b such that what? F prime of c equals fill in the blank. So I told you I'm not going to prove this right at the moment because, well, I know I haven't prepared. It's not something. This is one of those things that's just not natural for me, the proof of it. But it isn't very unsurprising result, because let me show you why this is plausible. Well, if this, let's draw the picture. What are we talking about? We've got a function. It's continuous on, let's say this is a and this is b, right? It's continuous on a to b. F of a, right, is equal to f of b. All right? And it's differentiable, right? Which means it's got no kind of jagged corners or something. So it has to look something like, I don't know, could look like a lot of different things, right? So it could be the straight line. What do you see? Well, if you look at this, the feature you should notice is it has to have turning points. It has to have places where the derivative is 0. And that's Rolle's theorem. I often, when I teach this, I often use, like, you know, let me find a cheaper chalk. I don't want to break one of my, oh, I'll use this thing, whatever this is. So, like, in physics, I may use the eraser. This is basically the statement that, you know, if you have something and it starts at this position, right, and then it comes back to the same position at the end of the time interval, somewhere in that time period, its velocity was 0, because it had to turn around. That's what Rolle's theorem says. So in some sense, it says what goes up must come down, if you want to think about it in terms of, you know, kinematics. All right, so anyway, I'm not going to prove that, except to give you that plausibility argument. I suppose some people would call that a proof, but I wouldn't. So I'll either go over the proof next class, or I'll post a little video on it, whichever I think is better for you guys, depending on where we get to today. Yeah. Okay, so in your homework, I have a question that says verify the mean value theorem, right? What does that mean? Well, let me show you how we verify Rolle's theorem. What's that instruction mean? Verify Rolle's theorem for f of x equal to sine x, better give me a closed interval, on 0 to pi. So what does it take to verify Rolle's theorem? To verify Rolle's theorem, we should check that the presuppositions of the theorem are met to start with, right? So observe, number 1, f of x equals sine x is continuous on 0 to pi, right? 2, f prime of x, which by the way is cosine x, right, exists on 0 to pi open interval, right? That's condition 2. Condition 3, f of 0 equals sine of 0 equals 0. F of pi equals sine of pi equal to 0. So condition 3 of Rolle's theorem is met, right? Now, how do we verify Rolle's theorem? To verify Rolle's theorem, we need to produce the value between 0 to pi, which makes f prime of x equal to 0. So you tell me, what x do we choose between 0 and pi to make a cosine of x 0? I mean, here's a graph of sine from 0 to pi. Right? So right in the middle is actually the point we're looking for, right? Because remember, cosine of pi over 2 is what? It's 0. So observe f prime of pi over 2 is cosine pi over 2 equal to 0. So we can see pi over 2 is an element of 0 to pi. Right? This verifies Rolle's theorem. So when I ask you to verify the mean value theorem, I mean for you to take that function and check that it satisfies the presuppositions of the theorem, right? And then find the C which the mean value theorem claims. Ah, the mean value theorem. Let us write it down, yes? Yep. Yeah, because the derivative of sine is cosine. Yeah. I'm just pointing out it exists, right? I mean, cosine, we know cosine works there. I mean, honestly, derivative of sine is differentiable on the whole real number system. So, like, of course, it's differentiable on a subset of it. You know, I mean, mean value theorem. Mean value theorem. So we like to abbreviate this for future purposes as MVT. All right? So this is very similar to Rolle's theorem, but not quite the same. Right? And here it is. Suppose f is a function such that, by the way, so like for the next test, theorems you should be able to quote would be, for example, Fermat's theorem, either version of it, Rolle's theorem, the mean value theorem. Like these are things we want calculus students to know coming out of this course, such that one, f is continuous on the closed interval from a to b. Number 2, f is differentiable on the open interval from a to b. All right. Now that's there's no condition 3 here this time. And here's the punchline. Then there exists C in a comma b such that f prime of c, I'll write it down here, f prime of c equals f of b minus f of a over b minus a. That is, there exists C in a comma b for which f of b minus f of a, curses, f of b minus f of a is equal to f prime of c times b. I'm just rewriting it again as a point of, convenience. You can either, the reason I'm writing that in the theorem is you may use either result as a consequence of the mean value theorem. So I'm freeing you of doing the algebra. Like you can jump straight to this as an application of the mean value theorem if you want. Of course, this equation and that equation are like algebraically the same. Yeah. Before I give you the formal proof, I would just show you a picture, try to kind of explain why this is true, right? So here's A, here's B, all right? And let's suppose our function looks something like like this, right? And maybe it's got some ups, maybe it's got some downs, but it goes like that, let's say, right? Now, f of b minus f of a over b minus a, that is the slope of the secant line which connects a and b. So this green line, this has slope f of b minus f of a over b minus a. It is the secant line which connects the point a comma f of a to the point over here, b comma f of b, right? So look at it. Is there a point in the middle where the tangent line is parallel to that line? See, because that's what this says. It says this slope and that slope are equal. That's the characterization of parallel lines. Well, look, you see it, right? Like right here. Or right in there somewhere, right? Or even down here somewhere there's a point. So these are choices. We could use this for C, we could use that for the C, we could use that for the C, right? If you'd like me to restate the mean value theorem in terms of physics, what it's saying is that the average rate of speed over a trip has to match the instantaneous speed at some time. If I go 60 miles an hour from my home to school, there is some point in that trip in which I was going 60 miles per hour. That's what the mean value theorem says. There's also other points where I'm going more like 85. Because I don't want that truck to squash me. You know? Anyway. All right, so let me show you the proof. And that'll be it for today. So we suppose f is continuous and differentiable on AB. We define h to be the function, which is the difference of the secant line. So the green line, they're saying this green line, y equals s of x is the green line. It's the secant line from A to B. So like s of x, the secant line. To get the formula for that, it would be like f of b. Well, how do I want to do it? F of, I'll use a. F of a plus f of b minus f of a over b minus a. That's the slope of the secant line, right? And then x minus a. So that's a formula for the green line. That's the secant line, all right? And then they're going to construct h of x to be the difference, all right? We want it to be the difference between f of x and the secant line. That makes a lot of sense if you start thinking about it, because we're trying to prove that there are points where the derivatives of the little blue lines have the same slope as the green line, you know? And that amounts to showing that f prime of c is equal to the slope of the secant line. So if f of x, so if we can show, if they have the same slope, then this is going to cancel out. We're going to have slope 0, right? But we know something about slope 0. We know we can use like Rolle's theorem to get our pause on that. So that's kind of the strategy here. But anyway, this is h of x. Now the formula for h of x specifically then is what? H of x is equal to f of x minus f of a minus f of b minus f of a divided by b minus a times x minus a. All right, great. So observe h is continuous on the closed interval from A to B, and we'll soon see it is differentiable on the open interval from A to B. That's already actually kind of apparent because f prime of x exists, and the rest of it's the formula for a line, right? We know we can differentiate a line with immunity. So like definitely the derivative of h exists on a to b because we're assuming the derivative of f exists on a to b. So it's continuous, it's differentiable. That's condition 1. Condition 2 for Rolle's theorem. Condition 3 for Rolle's theorem is what? What is h of a equal to? So I don't want to write it out, but look at the formula. What happens when we plug in a? F of a minus f of a, that's 0. And over here, a minus a is 0. So see, h of a is 0. How about h of b? So I'll write that one out. We have f of b minus f of a minus parentheses f of b minus f of a divided by b minus a times b minus a, right? So these guys be canceling. And then the difference of f of b and f of a likewise cancels, and we get 0. Aha! So Rolle's theorem exists. I mean, Rolle's theorem applies here, right? And what does Rolle's theorem tell us? What does Rolle's theorem tell us? There exists C in a to b such that what? H prime of C equals to 0, right? Now we haven't even calculated h prime of x yet, have we? Let's do that. H prime of x is what? H prime of x, it's f prime of x. That's a constant, it differentiates to 0. This is a number, so it just rides along. And what's the derivative of x minus a with respect to x? That's easy, right? What's the derivative of x minus a? Well, that's just 1, right? So put it all together, what we have is that f prime of c minus f of b minus f of a divided by b minus a, well, that's equal to 0. Which, one more algebra step, we have it, right? And that is the mean value theorem. Mean value theorem is very important. We'll see that that allows us to connect the positivity or the negativity of the derivative to increasing and decreasing, like explicitly next class, stuff like that. But of course, I'll also work examples from your homework if you guys ask me tomorrow. Wait a minute, tomorrow your homework is due. Wait a second. Well, see, I'd like to say I could take your homework Friday, but when I say people bring your homework in Friday, then they don't bring it in, and then I'm kind of in like an awkward spot. So like I figure I should collect your homework while you're there. But I mean, I'm totally willing to give you guys till Friday to finish the homework if that'd be helpful. But I really do want you to turn it in this week for your own sake. Like, I don't want these things to linger. We need to finish this homework because we've got to move on to this stuff, you know? But anyway, I digress. You're going to give it to me tomorrow? Okay. You might?